Alright, so let's try to locate the local and the relative mins and max points of a polynomial graph, okay, and then we will apply it in some sort of pretty interesting application problem. Alright, so the one that you're going to try straightforward, put this into the graphing calculator. It's a quartic equation. Alright, and find your local mins and maxes. Since this is to the fourth degree, perhaps you have yourself an absolute maximum. Let's go ahead and pause the video, type that in, check to see if you're getting this right. Okay, you're back. So here's the answers. So this one, it does kind of make a bra looking form anyway. So it has 3 of these extrema points. And one of them does turn out to be an absolute minimum point. Let me call up the graph here. There. Okay. So I can see one of these things, one of these minimum points dips down further, and that one's the absolute minimum. And it's at negative 2.28, comma, negative 9.61. So negative 9.61 is the absolute minimum value for that function. All right, and then we have 2 more humps. The next one, the one that's in the middle, is a relative maximum. Relative maximum, I do my little calculator steps on that. I get a negative 0.65 and the y value negative 3.47, and that negative 3.47 is the local maximum at that point. And then I have one more local minimum, 0.68 for the x value, y value negative 7.03, and negative 7.03 is the minimum value, the local minimum value. What's the absolute maximum? Well, it doesn't have one because both ends of this graph are pointing to positive infinity. Okay, so on the next exercise is actually an application, pretty interesting one. So let me give you the lowdown, give you the situation. While rooting around in your bedroom while looking for a lost library book, you come across a 24-inch by 24-inch sheet of some sturdy but flexible material of alien origin. How it got there is not important. What is important is that you believe that it will be the perfect material to construct an open box with locking tabs to hold all of your toys. You plan to construct this box by cutting congruent squares from each corner and then folding along the dotted lines as shown in this diagram. Boop. Okay, so here is your little piece of sturdy but flexible material of alien origin. It's 24 by 24. And what you're going to do, see the little grayed out part? You're going to cut out a square from each one of these corners. Each one of these corners, same size, maybe 1 by 1, 2 by 2, whatever. And the ones that are on the left and the right, you're actually folding that twice because this piece is a locking tab. So it'll fold in, and then your edges will fold in on top of it. Take a look at the diagram right down below it. Okay? So what I want you to do in this first one is to write yourself a function that describes the volume of this box in terms of x, in terms of that little square side length that you can cut out, and then find the domain. Remember, volume of a box, it's a rectangular prism, is so easy. It's length times width times height. So you'll have to figure out what are the length and the width and the height after you have folded it using this little diagram. So pause the video and give that a try. Well, what did you come up with? Here, take a look at the answer. So first of all, whenever you go to fold up this box, what you should realize is that you're going to get a height of x. Whatever that side length is that you cut out, it's going to be the height of your box. Okay, along this bottom edge down here, you're taking out 1, 2, 3, 4 of these little x's. So it used to be 24, but you're taking out 4 of those x's. So this middle length right in here is this 24 minus 4x. 24 minus 4x. Okay? So that's the bottom edge down there. And then you do the same thing along the other edge. So this one, you're only taking away 2 x's, one from each side, and so that's why that's a 24 minus 2x. So volume, length times width times height, it doesn't matter what order those things come in because it's all multiplication. So multiply it out. You do not have to expand it. Your calculator can handle that equation in factored form like this. Okay, so now let's talk about the domain of that thing. So in this situation, domain is really important because whenever you look at the graph, it's going to have, well, this is x times 4x times 2x. It's going to be x cubed. So it could have a couple of humps in there. It should have, as you will see, 2 humps. But we only want the local maximum. So we have to decide, where does the graph make sense? Well, the graph is only going to make sense for the values of x. Smallest it could be is 0. Not actually 0, but close to 0, right? Because if I don't cut anything, I just have that sturdy piece of alien material. Okay, and then the highest value is going to be, oh, that says 24. Ooh, that is a mistake. That should be 6. And let me show you how I got that. So this bottom edge is the most restrictive because we are taking 4 of the x's away. So they always have to be the same size. So what I did is I took the 4x and I set it equal to the length that it used to be is 24. The reason why is because that's the most each one of those could be if they all added up to the side length. Now you couldn't cut that box because there would be nothing left over for the box. So you divide by 4, that should be 6. So the maximum value there should be the 6. Okay, so we're not done with this one just yet. Now check out the next part of this. So use your graphing calculator to graph that function and then find the value of x, the side length of the square that's going to maximize the volume of this box, because you want to put the most amount of toys in this little box. Okay, so give that thing a pause and see if you can come up with the maximum value for the volume and the x value that's going to give that to us. Okay, so here we go again, and I do need to change this one more time because I copied and pasted it. It's a 6. Okay, so I put this thing into the graphing calculator, and the rough sketch of the graph is down there. Let me actually pull up the graphing calculator here. So it's typed in. Here's my graph, and I have just this one hump. This is only a portion of that whole cubic equation because it's supposed to keep going down this way, and it's going to come back up like this. Okay, so this is the only part that makes sense with this application. If you want to know what my window settings are, let me click over there. I went from 0 to 6. That was what my domain is. I can't go anything outside of that. And then for my y minimum, this is the volume, so I said the minimum volume would be 0, and then I just picked 1,000. I wasn't quite sure. If it didn't work out, you could always come back and change it. And then again, I just divide that by 10, so my y scales go by 100 each. So back on the little graph, and then you maximize, you find the maximum value right in there. And that's the point that's displayed here. So 2.54 comma 665. The x value is the x value of the square that you're going to cut from your little diagram there. And then the y value is the maximum volume. That's the biggest volume that we can get if we cut it and make a box like this. 665, and that should be in inches cubed. Wasn't that fantastic? That was pretty awesome. Good use of a bit of algebra. Okay, so you got one more objective. See there.